Have you ever wondered what's happening inside your computer when you load a program or video game? Well, millions of operations are happening. But perhaps the most common is simply just copying data from a solid-state drive or SSD into dynamic random access memory or DRAM. An SSD stores all the programs and data for long-term storage, but when your computer wants to use that data, it has to first move the appropriate files into DRAM, which takes time, hence the loading bar. Because your CPU works only with data after it's been moved to DRAM, it's also called working memory or main memory. The reason why your desktop uses both SSDs and DRAM is because solid-state drives permanently store data in massive 3D arrays composed of 1 trillion or so memory cells, yielding terabytes of storage, whereas DRAM temporarily stores data in 2D arrays composed of billions of tiny capacitor memory cells, yielding gigabytes of working memory. Accessing any section of cells in the massive SSD array and reading or writing data takes about 50 microseconds, whereas reading or writing from any DRAM capacitor memory cell takes about 17 nanoseconds, which is 3,000 times faster. For comparison, a supersonic jet going at Mach 3 is around 3,000 times faster than a moving tortoise. So the speed of 17 nanosecond DRAM versus 50 microsecond SSD is like comparing a supersonic jet to a tortoise. However, speed is just one factor. DRAM is limited to a 2D array and temporarily stores 1 bit per memory cell. For example, this stick of DRAM with 8 chips holds 16 gigabytes of data, whereas a solid-state drive of a smaller size can hold 2 terabytes of data, more than 100 times that of DRAM. Additionally, DRAM requires power to continuously store and refresh the data held in its capacitors. Therefore, computers use both SSDs and DRAM. And by spending a few seconds of loading time to copy data from the SSD to the DRAM, and then pre-fetching, which is the process of moving data before it's needed, your computer can store terabytes of data on the SSD and then access the data from programs that were preemptively copied into the DRAM in a few nanoseconds. For example, many video games have a loading time to start up the game itself, and then a separate loading time to load a save file. During the process of loading a save file, all the 3D models, textures, and the environment of your game state are moved from the SSD into DRAM, so any of it can be accessed in a few nanoseconds, which is why video games have DRAM capacity requirements. Just imagine, without DRAM, playing a game would be 3,000 times slower. We covered solid-state drives in other videos, so in this video we're going to take a deep dive into the 16 gigabyte stick of DRAM. First, we'll see exactly how the CPU communicates and moves data from an SSD to DRAM. Then we'll open up a DRAM microchip and see how billions of memory cells are organized into banks, and how data is written to and read from groups of memory cells. In the process, we'll dive into the nanoscopic structures inside individual memory cells and see how each capacitor physically stores 1 bit of data. Finally, we'll explore some breakthroughs and optimizations, such as the burst buffer and folded DRAM layouts that enable DRAM to move data around at incredible speeds. A few quick notes. First, you can find similar DRAM chips inside GPUs, smartphones, and many other devices, but with different optimizations. As examples, GPU DRAM, or VRAM, located all around the GPU chip, has a larger bandwidth and can read and write simultaneously, but operates at a lower frequency. And DRAM in your smartphone is stacked on top of the CPU and is optimized for smaller packaging and lower power consumption. Second, this video is sponsored by Crucial. Although they gave me this stick of DRAM to model and use in the video, the content was independently researched and not influenced by them. Third, there are faster memory structures in your CPU called cache memory, and even faster registers. All these types of memory create a memory hierarchy, with the main trade-off being speed versus capacity, while keeping prices affordable to consumers and optimizing the size of each microchip for manufacturing. Fourth, you can see how much of your DRAM is being utilized by each program by opening your computer's resource monitor and clicking on memory. Fifth, there are different generations of DRAM, and we'll explore DDR5. Many of the key concepts that we explain apply to prior generations, although the numbers may be different. Sixth, 17 nanoseconds is incredibly fast. Electricity travels at around 1 foot per nanosecond, and 17 nanoseconds is about the time it takes for light to travel across a room. Finally, this video is rather long, as it covers a lot of what there is to know around DRAM. We recommend watching it first at 1.25 times speed, and then a second time at 1.5 speed to fully comprehend this complex technology. Stick around, because this is going to be an incredibly detailed video. To start, a stick of DRAM is also called a Dual Inline Memory Module, or DIMM, and there are 8 DRAM chips on this particular DIMM. On the motherboard, there are 4 DRAM slots, and when plugged in, the DRAM is directly connected to the CPU via 2 memory channels that run through the motherboard. Note that the left 2 DRAM slots share these memory channels, and the right 2 share a separate channel. Let's move to look inside the CPU at the processor. Along with numerous cores and many other elements, we find the memory controller which manages and communicates with the DRAM. There's also a separate section for communicating with SSDs plugged into the M2 slots, and with SSDs and hard drives plugged into SATA connectors. Using these sections, along with data mapping tables, the CPU manages the flow of data from the SSD to DRAM, as well as from DRAM to cache memory for processing by the cores. Let's move back to see the memory channels. For DDR5, each memory channel is divided into 2 parts, Channel A and Channel B. These 2 memory channels, A and B, independently transfer 32 bits at a time using 32 data wires. Using 21 additional wires, each memory channel carries an address specifying where to read or write data, and, using 7 control signal wires, commands are relayed. The addresses and commands are sent to and shared by all 4 chips on the memory channel, which work in parallel. However, the 32-bit data lines are divided among the chips, and thus each chip only reads or writes 8 bits at a time. Additionally, power for DRAM is supplied by the motherboard and managed by these chips on the stick itself. Next, let's open and look inside one of these DRAM microchips. Inside the exterior packaging, we find an interconnection matrix that connects the ball grid array at the bottom with a die which is the main part of this microchip. This 2 GB DRAM die is organized into 8 bank groups, composed of 4 banks each, totaling 32 banks. Within each bank is a massive array, 65,536 memory cells tall by 8,192 cells across, essentially rows and columns in a grid, with tens of thousands of wires and supporting circuitry running outside each bank. Instead of looking at this die, we're going to transition to a functional diagram, and then reorganize the banks and bank groups. In order to access 17 billion memory cells, we need a 31-bit address. 3 bits are used to select the appropriate bank group, then 2 bits to select the bank. Next, 16 bits of the address are used to determine the exact row out of 65,000. Because this chip reads or writes 8 bits at a time, the 8,192 columns are grouped by 8 memory cells, all read or written at a time or by 8, and thus only 10 bits are needed for the column address. One optimization is that this 31-bit address is separated into 2 parts and sent using only 21 wires. First, the bank group, bank, and row address are sent, and then after that the column address. Next, we'll look inside these physical memory cells, but first let's briefly talk about how these structures are manufactured, as well as this video's sponsor. This incredibly complicated die, also called an integrated circuit, is manufactured on 300mm silicon wafers, 2,500-ish dies at a time. On each die are billions of nanoscopic memory cells that are fabricated using dozens of tools and hundreds of steps in a semiconductor fabrication plant, or fab. This one was made by Micron, which manufactures around a quarter of the world's DRAM, including both NVIDIA's and AMD's VRAM in their GPUs. Micron also has its own product line of DRAM and SSDs under the brand Crucial, which, as mentioned earlier, is the sponsor of this video. In addition to DRAM, Micron is one of the world's leading suppliers of solid-state drives, such as this Crucial P5 Plus M2 NVMe SSD. By installing your operating system in video games on a Crucial NVMe solid-state drive, you'll be sure to have incredibly fast loading times and smooth gameplay. And if you do video editing, make sure all those files are on a fast SSD like this one as well. This is because the main speed bottleneck for loading is predominantly limited by the speed of the SSD or hard drive where the files are stored. For example, this hard drive can only transfer data at around 150 megabytes a second, whereas this Crucial NVMe SSD can transfer data at a rate of up to 6,600 megabytes a second, which, for comparison, is the speed of a moving tortoise versus a galloping horse. By using a Crucial NVMe SSD, loading a video game that requires gigabytes of DRAM is reduced from a minute or more down to a couple of seconds. Check out the Crucial NVMe SSDs using the link in the description below. Let's get back to the details of how DRAM works and zoom in to explore a single memory cell situated in a massive array. This memory cell is called a 1T 1C cell and is a few dozen nanometers in size. It has two parts, a capacitor to store one bit of data in the form of electrical charges, or electrons, and a transistor to access and read or write data. The capacitor is shaped like a deep trench dug into silicon and is composed of two conductive surfaces separated by a dielectric insulator or barrier just a few atoms thick, which stops the flow of electrons but allows electric fields to pass through. If this capacitor is charged up with electrons to 1 volt, it's a binary 1. And if no charges are present, and it's at 0 volts, it's a binary 0. And thus, this cell only holds 1 bit of data. Designs of capacitors are constantly evolving, but in this trench capacitor, the depth of the silicon is utilized to allow for larger capacitive storage, while taking up as little area as possible. Next, let's look at the access transistor, and add in 2 wires. The word line wire connects to the gate of the transistor, while the bit line wire connects to the other side of the transistor's channel. Applying a voltage to the word line turns on the transistor, and while it's on, electrons can flow through the channel, thus connecting the capacitor to the bit line. This allows us to access and charge up the capacitor to write a 1, or discharge the capacitor to write a 0. Additionally, we can read the stored value in the capacitor by measuring the amount of charge. However, when the word line is off, the transistor is turned off, and the capacitor is isolated from the bit line, thus saving the data, or charge, that was previously written. Note that because this transistor is incredibly small, only a few dozen nanometers wide, electrons slowly leak across the channel, and thus, over time, the capacitor needs to be refreshed to recharge the leaked electrons. We'll cover exactly how refreshing memory cells works a little later. As mentioned earlier, this 1T 1C memory cell is one of 17 billion inside this single die, and is organized into massive arrays called banks. So let's build a small array for illustrative purposes. In our array, each of the word lines is connected in rows, and then the bit lines are connected in columns. Word lines and bit lines are on different vertical layers, so one can cross over the other, and they never touch. Let's simplify the visual and use symbols for the capacitors and the transistors. Just as before, the word lines connect to each transistor's control gate in rows, and then all the bit lines and columns connect to the channel opposite each capacitor. As a result, when a word line is active, all the capacitors in only that row are connected to their corresponding bit lines, thereby activating all the memory cells in that row. At any given time, only one word line is active because if more than one word line were active, then multiple capacitors in a column would be connected to the bit line, and the data storage functionalities of these capacitors would interfere with one another, making them useless. As mentioned earlier, within a single bank there are 65,536 rows and 8,192 columns, and the 31-bit address is used to activate a group of just 8 memory cells. The first 5 bits select the bank, and the next 16 bits are sent to a row decoder to activate a single row. For example, this binary number turns on the word line row 27,524, thus turning on all transistors in that row and connecting the 8,192 capacitors to their bit lines, while at the same time the other 65,000-ish word lines are all off. Here's the logic diagram for a simple decoder. The remaining 10 bits of the address are sent to the column multiplexer. This multiplexer takes in the 8,192 bit lines on the top, and, depending on the 10-bit address, connects a specific group of 8-bit lines to the 8 input and output I/O wires at the bottom. For example, if the 10-bit address were this, then only the bit lines 4,784 through 4,791 would be connected to the I/O wires, and the rest of the 8,000-ish bit lines would be connected to nothing. Here's the logic diagram for a simple multiplexer. We now have the means of accessing any memory cell in this massive array. However, to understand the 3 basic operations, reading, writing, and refreshing, let's add 2 elements to our layout. A sense amplifier at the bottom of each bit line, and a read and write driver outside of the column multiplexer. Let's look at reading from a group of memory cells. First, the read command and 31-bit address are sent from the CPU to the DRAM. The first 5 bits select a specific bank. The next step is to turn off all the word lines in that bank, thereby isolating all the capacitors, and then pre-charge all 8,000-ish bit lines to 0.5 volts. Next, the 16-bit row address turns on a row, and all the capacitors in that row are connected to their bit lines. If an individual capacitor holds a 1 and is charged to 1 volt, then some charge flows from the capacitor onto the 0.5 volt bit line, and the voltage on the bit line increases. The sense amplifier then detects the slight change or perturbation of voltage on the bit line, amplifies the change, and pushes the voltage on the bit line all the way up to 1 volt. However, if a 0 is stored in the capacitor, charge flows from the bit line into the capacitor, and the 0.5 volt bit line